Some other case studies, early warning of side slope bending. This is a pipeline in east of Toronto. So we installed the discrete strain gauges and we're tracking a lateral bending trend on a pipeline located in a moving slope in eastern Canada. FBG reported the increasing strain to the operator and a stress relief excavation was conducted at stage 3. So if you look at the graph on the right side of the slide, you can see the strain on the downsloped side of the pipe, the spring line, start to increase on point number 1. Point number 2, we're getting towards the red alarm. We actually end up exceeding it. That is when we shut down the pipeline and we implement a stress relief. So we're not actually replacing any of the pipe section. We're just relieving the stress by excavating it, that area, and then backfilling it again. We actually ended up pulling the pipe up slope a bit. And then you can see the strains collapse back to steady state, and then they continue on. So if the operator did not have some sort of instrumentation on the pipe, we kind of would be oblivious to the movement, and eventually that apex of that bend there, you can see in the middle of the photograph, that would essentially result in either a buckle or a highly compressive zone of the intradose, result in a potential leak. Another one, these are fiber optic Bragg strain gauges where we're tracking, this is in northern Canada, we're tracking an incipient buckling trend on a pipeline. Rapidly developing localized strain concentrations were detected at the intradose of the expansion loop bends due to downslope loading. So you can see on the plot there, for about 10 years or so, not much is happening. And then a couple of years ago, we started seeing quite a bit of rapid strain concentrations at the inner bend of the expansion loops. And once we looked into that, we did a bunch of analysis. We ran ILIs, we did FEA, we looked at the sloping clinometers, essentially a full engineering assessment, and the conclusion was that a buckling trend was developing, and the solution was to continue monitoring it until it reaches a certain level, red alarm, after which we will then potentially excavate. That you can also see our trending changes in pipe strain due to seasonal variation. So the pipe expands and contracts moves with the expansion and contraction of the surrounding soil based on winter and summer seasons. And you can see there the FEA that was done on that section of pipe. We do see strain concentration at the inner bend of the expansion loop. Early warning of pipe over a bend. Here's another fiber optic fiber Bragg strain gauge system where you can see there the first one where the line is forced into an overbend. This is monitoring longitudinal strain. Strain relief of the pipe section is implemented where we excavated the pipe. The line is then put back into steady state. We then bury the pipe, make sure that everything is back to normal, and then that buys the operator again more time to for remediation to keep monitoring. And we can see now that the crown gauges went back into tension, and we're going to probably have to do some more remediation. We can also use the fiber Bragg gauges for pipeline leak detection in addition to distributed sensing. So we're tracking rapid changes in pipeline surface temperature due to planned operations or potential loss of containment. And by installing discrete strain gauges in a circumferential orientation, we can monitor the hoop stress strain distribution around the pipe and detect small changes in line pressure, which can also potentially lead to or provide information about potential leak. So you can see there, the first one, everything is going okay, and then we see a big drop in the pipeline temperature differential. It is a routine pipeline shutdown, so we were aware of that. Everything goes back to normal, and then we have another routine pipeline shutdown that didn't go quite as planned as the first one, and we're able to see that by the changing delta T signature. Everything goes back in order, and then we, because of the strain on the pipe, we ended up actually shutting down the pipeline for assessment and remediation. You can see there they tried to shut down the first time, it didn't work, and then finally they got it, and the pipeline is then going under remediation. So once it's put back into service, the pipe delta T goes back to the baseline. typical pipeline monitoring data processing flow. I'm going to move a bit faster now. So we're looking at strain, deformation, displacement, temperature, and vibration. We're looking at getting the raw data in about less than 0.1 seconds, so pretty real time. Data collection and communications. The alarms go to the control room within 2 seconds if it's connected to a SCADA system, and then there's action within 3 seconds. So the field operations actions are entirely separate from engineering in the sense that they're not waiting around for engineering to tell them what to do. If it is a red alarm, then a red alarm equals shutdown. As long as the alarm is confirmed by Weir Jones, they go ahead and do that shutdown. At the same time, numerical data is sent within 4 seconds to the head office and our servers, and a graphical report on a custom portal is available to the client within 10 minutes. Process data is provided to the pipeline integrity team and their engineering consultants, and the stress model is then refined and on an ongoing basis. So on the left side, you have your operations, and on the right side, you have your ongoing engineering and integrity management. We'll briefly touch on design and constructability. Our fiber optic sensing cables can be attached or adhered to the pipe using various methods specific to an installation. We are primarily interested in detecting deformation trends in and around a pipeline as a precursor to loss of containment. The key to obtaining reliable data is to ensure that you have good strain transfer between the pipe and the sensing cable. So if you have a sensing cable next to the pipe, that tells you what the ground is doing around the pipe, but not necessarily what the pipe is actually doing. So we want a one-to-one comparison directly on the pipe. The good thing about fiber optic sensing cables is you don't have to remove any of the fusion bonded epoxy coating. So it's minimally invasive. During engineering and design phase, WJE develops an installation plan that is fully integrated into the overall pipeline construction plan and schedule. And of course, we can do it in any season. Typically in Canada, we do this installation in the fall or winter. And our installation rate typically is similar to the pipeline welding rate, and it's fully integrated into the pipeline construction plan. We do a lot of testing and calibration. We are an R&D engineering firm as well. Everything is NIST traceable. We test our custom fiber optic sensing cables for performance at our facility here, including a optical test bench where we are able to apply large loads and deform the cables to mimic what the pipe would do. We have the ability to do temperature sensing in our environmental chamber. We can do ranges from -73 to 177 degrees. These are some samples of discrete sensors. So depending on what we're looking for, we orientate the gauges at different axes, whether it's axial strain or circumferential. And you can see some of our fiber optic racks there. This one actually has on the far right fiber brag grading system, as well as a distributed strain and temperature monitoring system. We also build custom portals for clients where you have alarm dashboards and you can monitor and track various parameters. We also pipe in geotechnical parameters. So weather stations where if you have a rainfall alarm, a rainfall over, for example, 40 millimeters in a day, that triggers a geotechnical assessment. That alarm, you can see on the top right there, is sent directly to a geotechnical team. So we can do quite a bit with our custom portals. These are some more examples. Structural integrity monitoring, non-pipeline, distributed fiber optic strain and temperature sensing can be effective in monitoring the long-term integrity of concrete installation by attaching sensing cables to the rebar structure prior to pouring. Load assessment, to conduct load assessment of specialty concrete structures. We monitor the continuous temperature during pouring and curing to make sure everything is as the structural engineers expected. And then ongoing monitor deformation during pre-stressing and loading, and then concrete aging and cracking. I'm going to fly kind of through this, running a bit out of time, but we do a lot of structural integrity monitoring of gas lines as well. So we do the field measurements, collect the data, do the model, conduct the FEA in conjunction with the operator or the pipeline owner, and determine what the the concerns are. So here's some images. Another one is of a underground structure at a mine where we put different strain gauges on to look at an issue they've had with vibration and loading. We're looking at the collapse mechanisms. This is another one where we're using fiber Bragg strain gauges installed on a rail tippler in an explosive environment to monitor strain fatigue. And you can see there long-term fatigue analysis was carried out to assess effects of reversing loads. So you can see the rail tipplers loading and unloading, and we can monitor that in real time with fiber optic strain gauges. So conclusion. Significant commercial and reputational risks exist when projects are constructed in environmentally sensitive areas where geotechnical and structural hazards exist. FBG's structural integrity monitoring systems are designed to meet specific project requirements and local conditions. They provide quantitative data for a wide range of parameters. We're interested in strain, temperature, deformation, displacement, both vertical, horizontal, and the differential, piezometric pressure, weather anomalies, and all of that provides early warning of potentially hazardous conditions to the structure and the surrounding environment. Fiber optic sensing technologies provide a reliable method of collecting data in real time and assessing the integrity of the structure in a proactive manner. FBG integrates quantitative operational information, allowing the identification and mitigation of a risk in a timely manner before a leak or loss of containment occurs, not after. And finally, transparent structural integrity monitoring systems on your assets diffuse adverse public reaction to pipeline projects. We found that the operators that say we have monitoring systems on the pipe have a much nicer conversation with the community than ones who say we're doing it intermittently or as an issue occurs. Thank you very much. Thank you, FOSA, for the opportunity to present. And at this time, if you have any questions, we'll be happy